Hi everyone! So in my last video I talked about index numbers, what they are and how they can be used to show repeated multiplication in a shorter and easier way. If you haven't checked out that video yet and you don't know the first thing about index numbers, I suggest you check out that one first. Otherwise, if you've already seen it or if you already kind of have an idea of what index numbers are and you just want to know how to work with them, then this is the video for you, so keep watching. First off, when do we actually use index numbers in real life? In most everyday life examples, the kind of maths you'll be working with will be linear mathematics, where numbers grow or change at a constant rate. So, for example, if you were going to buy an ice cream and each ice cream costs $3, then the more ice creams you buy, the more money you'll have to pay, but you'll be paying that extra money at a constant rate. So, for example, if you bought one ice cream, you'd pay $3. If you bought two, you'd pay $6. 3 ice creams would be $9 and so on. You can also think of it as the money you have will decrease at a constant rate of $3 per ice cream if you want. The point is, the rate of change will be linear or consistent. In our example, the money we have or the money we spend will change depending on how many ice creams we buy, but the change will be constant, steady. So if that's a linear rate of change, what does an exponential rate of change look like? You might have actually heard this before, especially when people want to emphasize how much or how quickly something is transformed. Our sales have increased exponentially, an employee might say to his boss. What does that actually mean though, exponentially? When something changes exponentially, the rate of change is not consistent. The increase or decrease gets more and more rapid the further you go. Bacteria is an example of something that grows in exponential fashion. On the first day, you might just have one bacterium. On the second day, it multiplies and you have 2. Then the next day you have 4. And then you have 8. And then 16, 32, 64. See how with each day the amount of bacteria you have doubles, and see how they're growing at an increasing rate, not a constant rate? If the bacteria were growing at a constant rate, you'd see them increasing steadily like this. But this growth rate is getting faster and faster with time. Another good example of exponential growth is the zombie virus. At first you might have just one zombie, but if it bites 3 people and they become zombies, and if each zombie then bites another 3 people, then it won't take long before your city is overrun with zombies. That's why in the movies they often show it only takes a few weeks or 28 days before there are zombies everywhere. And here's a visual example of exponential growth.
Oh! Mom? Aunt Willow? What? We have a problem. Working! We have a plan B, right?
Now here's a quick question. Which of the following examples demonstrates exponential change? If you said B, you were correct. I hope this helps gives you an idea of how exponential problems arise in real life and how to recognize them. And now we're up to the next question. How do we actually translate these real-life situations into mathematical equations with index numbers? Let's take a look at the zombie apocalypse example. We start with just one zombie. It only takes one to start an epidemic. After 1 day, we have 3 zombies. After 2 days, we have 9 zombies. After 3 days, we have 27 zombies. Can you see the pattern? What's happening to the number of zombies with each passing day? If you said each day there's 3 times as many zombies as the day before, you'd be correct. You can see how the number of zombies gets tripled as you go. So how do we show this in writing? With numbers. Well, remember how I said before that index numbers are used to show repeated multiplication? If we have a look at index numbers again, an index number is made up of a base, which is a number being multiplied, and an exponent, which is how many times we have to multiply that number. Here, in our example, we are multiplying by 3 each time. So our base is going to be 3 times 3 times 3 times 3 and so on and so on. The exponent is how many days have passed since the first person became zombified. So stay with me here, this might get a little tricky. After 1 day, we have 1 3 to multiply. So it's just 3 to the power of 1, or 3 zombies. After 2 days, we have 2 3s to multiply. So that gives us 3 times 3, or 9 zombies. And after 3 days, we'll have 3 to the power of 3, or 3 cubed. 27 zombies. Most of the time, when you're dealing with index numbers in real life, this is how it will look like. The base will be the rate of change, such as in the zombies example, they were tripling with each new wave, and with the bacteria example, we were doubling. In real life, the exponent is usually going to be a function of how long have you been multiplying at that rate. So going back to the zombies example, we can work out exactly how many zombies are going to be around if we know the rate of change and how much time has passed, or how many changes have occurred. So for example, if we have a zombie apocalypse situation where we know the number of zombies keeps tripling every day, and it's been 8 days since the initial outbreak, how many zombies would we have? Well, we have 8 days, and we're multiplying by 3 each day, so we'll have 3 times 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 3 equals 6,561 zombies. Whew. These concepts can be a little bit tricky to get your head around, so you might like to rewind a little bit and just rewatch certain parts if you found anything a little bit confusing. But I'm going to wrap up this video now. It's taking a bit longer than I thought it would take. I'll take this opportunity though to explain something that a lot of people find a little bit baffling, that a number to the power of 0 is 1, not 0. A lot of people get confused about this. If 3 to the power of 0 means that there are no 3's being multiplied, shouldn't the answer be 0? Why is it 1? Where'd the 1 come from? Well, if we understand that the base is the rate of change and the exponent refers to time, then this suddenly makes a lot more sense. Going back to our zombies example, that's like saying, imagine we have a zombie apocalypse where the number of zombies will keep tripling every day, and it's been 0 days since the initial outbreak. The initial outbreak just started. The zombie hasn't infected anybody else yet. How many zombies would we have? Well, we'd have 1. We'd have that one lonely little zombie. You can also look at the basic pattern written out. If 3 to the power of 1 is 3, 3 to the power of 2 is 9, and so on and so on, you can see how as we're increasing the exponent, we're multiplying by the base, which is 3. Logically then, as we're going backwards, we're dividing by the base. We're dividing by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. So to get 3 to the power of 0, we'll have 3 divided by 3, which is 1. I'm going to end this video now by asking you one final question. Looking back at this table, this pattern, what do you think 3 to the power of negative 1 would be? Have a think about it, write down your best guess, and come back next time to see if you got it right. Thanks for watching, everyone. Hope you enjoyed my video. I'm going to be trying to post on a regular basis, so one video a week, hopefully. So if you're interested or if you'd like to show some support, then please like and subscribe. And I'll see you next time at Sneezy Teachers.